Okay. All right. So welcome back, folks. Once again, a good morning, good afternoon, good evening, whichever part of the world we are logging in from today. After a 1 month hiatus, I guess it was an unavoidable intermission, I would say, but we are back, and we are so delighted and honored to have our speaker today, Professor Charles Kane. Professor Kane is a theoretical condensed matter physicist and is the Christopher H. Brown Distinguished Professor of Physics at UPenn. He's globally renowned for theoretically predicting the quantum spin Hall effect, and what would later be known as topological insulators. In 2012, he was a co-recipient of the Dirac Prize, along with Duncan Haldane from Princeton, who was our previous speaker, and the late Shusheng Zhang, for their work on 2D and 3D topological insulators. The same year, he was part of the inaugural class of Math and the Physical Sciences Simons Investigators. He also is the 2012 recipient of the Oliver E. Buckley Prize. He is a co-recipient of the Physics Frontiers Prize with Lawrence Mollenkam and Shusheng Zhang for their work on topological insulators in 2013. In 2018, he shared the Frontiers of Knowledge Award with his colleague at UPenn, Eugene Mele. In 2019, he got the Breakthrough Prize in Fundamental Physics with Professor Eugene Mele for his work on topological insulators. And I could not resist the temptation, being a string theorist, on a stringy note, possibly not a lot of us would be aware of the fact that in his spare time, Professor Kane likes to listen to and play classical guitar music, and also collects guitar sheet music. And if you go to his website, he calls them some amateur recordings, but I think that's just him being modest. It's a very cool set of recordings. If you want to try them out. So anyways, back to physics. So with that short intro, I would request very humbly Professor Kane to please deliver his lecture.
Okay, so let me share the screen here. Okay, well, thank you so much for this, for that very generous introduction. So it's really a pleasure to be able to take part in this. I love to travel. I really wish I would have loved to, travel to India to do this. But this is the next best thing that we can do. So what I want to do, today is to tell you about some of the amazing things that matter can do. So, matter, of course, is the stuff that everything is made out of. And I'm going to be, talking mostly today about electronic matter, electronic materials. And in order to get started with that, I want to go back all the way to the very beginning, back to Benjamin Franklin. Okay. Now, I have to confess, I come from the University of Pennsylvania in Philadelphia, and Benjamin Franklin is a big deal there. Okay, we talk about Ben Franklin all of the time, but you see, so Benjamin Franklin is also very famous in the United States of America because he was one of the founding fathers. He was a statesman and one of the founding fathers of the United States. But in addition to that, Benjamin Franklin was really quite a Renaissance man. And in addition to being a statesman, he was also a scientist. And as a scientist, Benjamin Franklin was famous for his observations of one of the most fundamental aspects that matter has, which is he did the first systematic observations of the phenomenon of electricity. Okay, and so electricity is the stuff that lightning bolts are made out of. Okay, it's also what makes your socks stick together when you take them out of the dryer. So electricity is a ubiquitous phenomenon, and so Benjamin Franklin is famous for these experiments that he did, where he went out into a lightning storm and flew a kite. Okay, now. I don't recommend that you try that at home. It's remarkable that he survived doing that. But in doing so, he made a remarkable observation about the physical world, which is that matter has an attribute which he called electric charge. Okay, and he recognized that electric charge can be positive or it can be negative, and like charges push each other apart, and opposite charges attract each other. Okay, and so this is a deep and fundamental thing about matter. He also recognized that there are basically two classes of materials. There are materials that we call conductors that can transmit electric charge, kind of in the same way that water flows in a pipe. And there are other kinds of materials that do not transmit electric charge, and those are electrical insulators. Okay, and so there's a fundamental dichotomy between these different types of materials. Now, so this was a deep and fundamental observation about the fundamental building blocks of matter. Okay, but I want to make a point that Benjamin Franklin, in addition to being a deep thinker, he was also a very practical man. Okay, and so Franklin realized that with this new knowledge, he could do something incredibly useful. Okay, and so this allowed him to invent one of the most important technologies of his day, which was the lightning rod. Now, of course, the lightning rod is the way you keep your house from burning down in a lightning storm, by sort of shorting the electricity around your house into the ground. Okay, and so this to me is epitomizes what is best about science. Okay, so on the one hand, it is deep, it is beautiful, it is fundamental. On the other hand, it's useful. Okay, and this interplay between useful and deep and beautiful is what has driven discoveries over the past 250 years. Okay, and boy, what a ride we've been on in the last 250 years. So let's fast forward to the present day, and today we have electronic materials that can do the most amazing things. Okay, so just think about it. Really, it's like magic, right? You can have a powerful computer in your pocket. Okay, I can talk to you from halfway around the world. This is truly amazing. Okay, and the reason that we can do this is because of the understanding that we have, the understanding and control over the electronic structure of matter. Okay, and so these discoveries and our understanding of electronic matter have enabled the technologies that we've grown accustomed to in the information age. Okay, and so what I'd like to tell you about today is that these discoveries that about the fundamental properties of matter, they're continuing to develop, they're continuing to evolve. Okay, and I'd like to tell you about some new electronic phases of matter. Okay, that may enable new technologies in the coming century. Okay, so I want to show you how these new phases of matter lead to something new, and show you what they can be useful for. And I'd like to also try to share with you that they are incredibly beautiful and very interesting to think about. Okay, and so I want to spend some time thinking about phases of matter. Okay, and the most familiar phases of matter that you learn about in school are the liquid and the solid phase, say, of water. Okay, and so water can be a liquid, or if it freezes, it can be a solid. Okay, now there's something remarkable about this, because the building blocks of water, the individual water molecules, they're pretty simple. Okay, and they're all kind of the same. Okay, but just knowing and knowing how the building blocks operate. Okay, knowing the forces and what individual water molecules how they operate. That's part of the interesting story. Okay, but it's not the whole story. Okay, because another interesting thing is what happens if you have lots and lots of water molecules. What new phenomena can emerge from that? So what can you make out of those fundamental building blocks? Okay, and water can be a liquid that can flow, or it can be a solid that's rigid. Okay, and somehow those phenomena emerge from these very simple building blocks. Okay. Now, with regards to electronic matter, we also have electronic phases of matter. So, for instance, if you have an electrical wire, you have the copper wire is an electrical conductor. It allows electricity to flow. So that's one electronic phase of matter. Whereas the rubber that surrounds it is an electrical insulator that doesn't allow electricity to flow. Okay, and so these are two kinds of electronic phases of matter. And what I want to show you is that thinking about these electronic phases of matter has led to some deep and new ideas in physics that are the foundation for this new understanding that I want to describe to you. Now, so in order to get started with this, what I want to do is I want to start off by describing to you the fundamental building blocks that matter is made out of. Okay, and so this is the physics that came into focus at the beginning of the last century, around the beginning of the 20th century. There was a revolution in the way we understood the structure of matter. Okay, and so what emerged from that was the idea that matter is composed of fundamental particles. Okay, and the most important fundamental particles for these purposes are the electron, the proton, and the neutron. Okay, and the electron and the proton, the important thing about them is that they have electric charge. Okay. Now, there's something important about this, which is that every electron has exactly the same charge. Okay, and it has exactly the same charge as every other electron. In fact, and that charge is equal and opposite to the charge of the proton. Okay, so electric charge comes in discrete quantized units. You can't have half of an electric charge. Okay, that's against the rules. Okay, electric charge comes in these discrete units of E. Okay, actually, there's a funny story about this. Benjamin Franklin, I told you, he discovered charge. He discovered that charge could be positive and negative. So he was the one who got to decide which one is positive and which one's negative. Okay, now of course, Ben Franklin didn't know anything about electrons. So he made his choice, and he made the most unfortunate choice he could have made. Okay, because his choice made it so that the electron is negatively charged. Okay, and this is a fact which is a source of endless confusion for beginning physics students who are trying to solve problems when they realize that the electrons are flowing this way, but the electric current is flowing the other direction. Okay, and so that minus sign is something that you have to keep track of, and is a source of confusion. Now, so that's too bad. We're stuck with Ben Franklin's minus sign, so we just have to make do. But the important thing is that matter that charge comes in these discretely quantized units. Now, of course, electrons, protons, and neutrons, they arrange themselves into atoms. Okay, and atoms, you can think of an atom as being like a little solar system where the electrons are orbiting around the nucleus, which has the neutrons and the protons, sort of in the same way that the planets orbit around the sun. Okay. But this picture is actually incomplete due to another one of the revolutions that happened in the beginning of the 20th century, and that's quantum mechanics. Okay, and so what quantum mechanics teaches us, so quantum mechanics sort of drastically changed the way we think about the way electrons behave in atoms. Okay, and the simplest way of thinking about what it teaches us is to say that in an atom, the electrons can only occupy discrete quantized energy levels. So what this means is that the electrons in an atom, it's like they're snapped into place. Okay, they're snapped in, and there's no, they can't wiggle. There's no play for them to wiggle around. Okay, they're snapped in. It's sort of like I don't know if you had these toys. I grew up with these toys called Legos, where they're these building toys where you have these blocks and you snap them together. And once they're snapped together, then they're rigid and they can't move. Okay, and so the electrons sort of snap into place into atoms in the same way. And so what we say, so in order to get the electron to do anything, you have to give it a sort of a kick that is big enough to unstick it. Okay, and what we call this barrier to unsticking the electron, we call that the energy gap. Okay, so there's an energy gap, which is the barrier you have to overcome in order for the electrons to do anything, in order to unstick them from where they're sitting. Okay, now this observation that the electrons are sort of snapped into place in atoms allows us to understand the most basic electronic phase of matter, which is the electrical insulator. Okay, so let me show you a cartoon. So here are a bunch of atoms, and they each have their, the nucleus and the electrons, and the electrons are snapped into place in their, on each atom. So the electrons are sitting there, they're stuck in place. They're not doing anything. They're just stuck there. They can't do anything. So, there's a sense in which the insulating state is the most boring state, right? The electrons, they're not doing anything. They're just stuck in place and nothing's happening. Okay. Now, it's actually a little bit more interesting than that, because one thing you can do in an insulator is you could add an electron. Okay, so I added an extra electron. Okay, and if you add an electron, importantly, this electron, it has a precise charge E, minus E, because of Benjamin Franklin, right? But the thing is that this added electron has already paid the energy barrier. It's already paid the energy cost. So this electron can move around. Okay, so it can hop from atom to atom. It can flow. Okay, so if you add electrons to an insulator, then it becomes a conductor. It can conduct electricity. Okay, and so that's a kind of interesting fact. Now, but there's something else that you can do. Okay, and this is even maybe a little bit more interesting. So you could add an electron. The electron can move around. The electron is a sort of excitation of the insulator, but you can also remove an electron. Okay, now if you remove an electron, then you've sort of taken away a charge minus E. So it's like you've subtracted it. And so this missing electron, which we call a hole, has a charge plus E, opposite to that of the electron. Okay. But the thing that's interesting about this is that this hole is like a particle too. It can also move around and conduct electricity. So watch. So the hole can move by having the electron next to it take its place. There, it moved. Okay, it can move again. It can keep hopping. Okay, And so this is something that's new. So the hole is like a fundamental excitation of this insulator, which is like a particle that can move around. But this particle is an emergent particle. It wasn't part of the original building blocks that the insulator was made out of, right? The fundamental building blocks were the electrons and the protons. The protons aren't moving around. They're stuck in place, okay? But this hole is a positively charged particle that can move around, okay? And so so this is something that's new, okay? That you can have emergent particles that are, in a sense, they're just as fundamental, but they can only live inside the material, okay? Now, so you might think that if you could have an insulator and add electrons or holes to it to make them conduct electricity, you might think that that could be kind of useful, okay? So in fact, a material that it is easy to add electrons and holes to, an insulator that it's easy to add electrons and holes to, is called a semiconductor, okay? And semiconductors are useful, okay? So silicon is a semiconductor. Silicon is the semiconductor that is in all of the computer chips in all of your electronic equipment. Okay, and now, of course, silicon is a real material. It's more complicated than this cartoon picture that I've given you. Okay, but this was one of the great triumphs of the quantum theory of matter over the course of the 20th century. So over the course of the 20th century, we developed a very detailed understanding of materials like silicon, okay, understanding of their electronic properties. So silicon, so it's a crystal, it has a particular arrangement of atoms, okay, that has, detailed arrangement of atoms that we understand. And it has a very specific structure to its electronic excitations. Okay, now I don't want you to worry about what all the wiggles on this graph mean, okay? The point I want to make is that it's complicated. There are lots of details, okay? But these are details that we have come to understand very well, okay? And that detailed understanding has allowed us to harness these materials to do the amazing things that they can do, okay? And so this understanding, this detailed understanding of the electronic properties of materials is the foundation for electronics technology. Okay, and I want to show you that that we're still developing new understandings of these electronic properties of different kinds of materials. Now, but there's a point I want to make. So things are complicated. But I want to make the point that there's a sense in which this cartoon picture that I showed you, that was kind of easy to understand, right? And I'd like to argue to you that there's a sense in which that cartoon picture is right, because even in silicon, real silicon, it's still true that the fundamental carriers of electric charge are charge minus E electrons and charge plus E holes. So that's still true. So somehow this cartoon picture that I gave you gets that right. Okay, and so this leads to me to something which is very deep and beautiful about physics. Okay, which I'd like to try to share with you. And the way that I like to say it is that theoretical physics is like an impressionist painting. Okay, so what I mean by that, so look at this painting. It's it's kind of nice, beautiful painting. If you look at it too closely, though, if you go right up to it and look at it very closely, it's all wrong, right? It's not a reproduction of reality. Okay, the colors are all wrong. They're just little dots of things. It's not really right. But if you step back from it, there's a sense in which it captures the essence of the moment. Okay, and I'd like to argue to you that theoretical physics is kind of the same way. Okay, so we have these very simple descriptions, these simple models. Okay, and in detail, they're not exactly right. Okay, but I'd like to argue there's a sense in which they get things right. And I want to make the point that understanding the sense in which theoretical physics gets things right is a deeply aesthetic experience, okay, which I'd like to try to share with you a little bit. Okay, and so in order to try to explain the sense in which it gets things right, I want to introduce a beautiful concept, which is the concept of topology. Now, topology is it's a beautiful branch of mathematics, and topology is concerned with objects whose shape can be continuously deformed. Okay, so imagine that you have clay, and clay you can smoothly stretch it and squeeze it and change its shape continuously. And so what a topologist is interested in is topologists are interested in whether or not shapes can be continuously deformed into one another. Okay, and so the classic example for this is to think about the sense in which a coffee cup is the same as a donut. Okay, so a coffee cup, this is clearly a coffee cup, and this is clearly a donut. Okay, but if you imagine that it was made out of clay, you could very smoothly and slowly deform the shape of the coffee cup, and at each step, not very much is happening. I'm just changing it a little bit, at each step. I can do it completely continuously, and at the end of the day, it's become the donut. And you can sort of see the handle in the coffee cup turned into the hole in the donut. Okay, so a topologist would say that a coffee cup and a donut are the same. Okay, but that doesn't mean that everything is the same. Okay, so if you have a sphere like the surface of this orange, okay, you could deform that as well if it was made out of clay. You could squeeze it down. You could step on it and turn it into a pancake. Okay, but you can't turn it into a donut without poking a hole in it. Okay, and poking a hole is against the rules because you can't do that continuously. You have to go from not having a hole to having a hole suddenly, and that's a discontinuous process. Okay, so these are different, and so what topologists like to do is they like to come up with some simple way of characterizing whether things are the same or they're different. And in this case, there's a simple what we call a topological invariant, which is a number that you can associate with any surface, which basically in this case just counts the number of holes. Okay, so a sphere has genus 0 and a donut has genus 1. Okay, and this integer genus is something, it's an integer. It can't change continuously. It can only change suddenly. Okay, and so this is the idea of topology. Now, so you can ask yourself the question, okay, so this seems sort of a little bit, like some abstract mathematical thinking. What does this have to do with electronic phases of matter? Okay, now, so what I'd like to argue to you is that the sense in which this cartoon picture of the insulator gets it right is in the sense of topology. Okay, because insulators can be continuously deformed as well. Okay, and so let's imagine. So I want to introduce this idea that insulators are topologically equivalent to each other if they can be continuously deformed into one another while remaining an insulator. Okay, so we can imagine starting off with with silicon, the real silicon that has this really complicated electronic structure. okay? And so what you can imagine doing is you can imagine in your mind's eye, you can imagine slowly pulling the atoms in the silicon apart. So sort of, expanding it so that the atoms are getting further and further apart. And once you've gotten them really far apart, then the atoms are basically just independent atoms. And you've gone to a situation that looks much more like this cartoon picture. Okay. And if along the way it remains an insulator, then there's a sense in which this real insulator is the same as this cartoon insulator. Okay, and everywhere along the way, the fundamental charge carriers are the charge minus E electrons and the charge plus E holes. That stays the same. Okay, so there's a sense in which this gets it right. Now of course this cartoon picture is a lot simpler than the complicated thing. So it's like for surfaces, the sphere is the simplest surface that doesn't have any holes in it. Okay, but surfaces don't have to be simple. Okay, they could be more complicated. So this is Dave the octopus. Okay, and Dave the octopus has a more complicated shape. Okay, but I don't think he has any holes in him. So topologically, Dave the octopus is the same as the sphere. Okay, and so there might be some things about Dave the octopus that are easier to think about if you think about the sphere. Okay, and so that's the power of topology. Okay, and so now, most insulators are topologically equivalent to this trivial insulator, like silicon. Okay, so they're like the trivial, they're sort of like the sphere. Okay, but when you draw the picture like this poses a interesting question, which is, are there analogs of the donut? Okay, are there topological insulators that are not equivalent to the trivial insulator? In pictures, are they like the donut? Okay, the remarkable answer to this question is yes, and these are fascinating phases of matter that I want to introduce you to. But one point before I go there, the quantum theory of matter has been around for a long time. It's been around for 80, 90 years. Okay, and for a long time, nobody thought to ask this question. Okay, it wasn't obvious that you should think about electronic structures of materials in terms of topology. But once you pose this question, okay, then you're led along a path of discovery that has remarkable things to uncover. Okay, and so those are some of the things that I want to show you. Okay, so in order to sort of introduce you to the concept of topological insulators, what I always like to do is I always like to start with the simplest example of something, which is simple enough that hopefully you can get your head around what's going on. Okay, and the simplest example that I can think of for a topological insulator is a one-dimensional insulator called polyacetylene. So polyacetylene is a polymer. Okay, and so what a polymer is it's a one-dimensional chain of atoms. So polyacetylene is a chain of carbon atoms, and then there are hydrogen atoms attached. They're not so important, but the main thing is that it's a one-dimensional chain. And the thing that's interesting about polyacetylene is it's an insulator, but the reason it's an insulator is because what polyacetylene wants to do is it wants to dimerize, by which I mean it wants every other pair of atoms wants to bond to its neighbor a little bit more strongly. So so each pair is going to be a little bit closer together than the other pairs. So these double bonds are a little bit closer than the single bonds. Okay. And by dimerizing, it's able to, it becomes an insulator, an electrical insulator. So the electrons are snapped in place. But the thing that's interesting about this is that there are two ways you can do it. Okay. Because you can either have the bonds alternate, strong, weak, or they can alternate weak, strong, weak, strong. Okay. And so what I would like to argue to you is that these two distinct insulators are topologically distinct in the sense that I explained to you, which meaning that you can't get from this one to this one continuously, keeping it an insulator the whole time. Because if you want to go from here to here, what you have to do is you have to go through a point where all the bonds are the same. And when all of the bonds are the same, it's not an insulator anymore. Okay, it becomes a conductor. And so so these phases are different. Now, so the kind of impressionist picture that I'd like you to have of what's going on with this is that it's I told you in an insulator you have electrons that are sort of snapped in place into the atoms. Okay, so in this case, what you have is you have twice as many spaces for the electrons to sit than there are electrons. So the electrons are sitting in every other space. Okay, and so in the A phase, they're sort of sitting in the blue spaces. Okay, snapped in to the blue spaces. And in the B phase, they're snapped into the red spaces. Okay, and now an important thing I want to say about this is that overall, matter is overwhelmingly electrically neutral. There are just as many electrons as there are protons. Okay, and so so when in this insulating state, there are just enough protons to compensate the charge of the electrons. So this insulator is electrically neutral. Okay, so the charges of the electrons are compensated by the charges of everything else. Okay, so we have these two phases. You can sort of say, okay, so what? Okay, so we have these two phases. What does that buy us? Okay, so what new phenomena emerges from this? And in order to show you this, I want to show you a magic trick. Okay, so here's my magic trick. Okay, so I'm going to start off, and I have my nice chain of polyacetylene, which I can think in this cartoon. I have every other space, all the blue spaces have electrons snapped into them. Okay, and this is completely electrically neutral. Okay, so what I'm going to do is I'm going to add an electron. Oop, there it is. Okay, so now I have an extra electron. And, the electron has a charge of E, minus E, Benjamin Franklin, right? Okay, so now this situation has a charge exactly minus E. Okay, so now I've added all the charges I'm going to add. Now all I'm going to do is I'm going to rearrange things a little bit. And so, so what I'm going to do is I'm going to move things. So the first thing I'm going to do is I'm going to take these electrons and I'm going to move them over like that. Okay. And then I'll do it again. Move these ones over like that. Okay. And, I can keep doing that over and over and over again, moving things over further and further apart. Okay. Now, so I want to ask you a question. What happened to the charge minus E that I added? What happened to that charge? Okay, now, okay, I know there's probably some smart people out there who are gonna say it's right there. Okay, you're right. But think about it. In this region in the middle here, every other space is filled, right? So this is just like the electrically, it's electrically neutral in the middle here. There's just enough electrons to compensate the background charge. Okay, so there's no charge in the middle here. The only place there's electric charge is sort of where the electrons are bunched together, and that's here and here. Okay. So the charge is in two places, and this place here looks just like this place here. So the charge has to be the same. And so what has happened when we added the electron is it is split in half. Okay, there's an exact charge E over 2 here. Okay, and this charge E over 2, it's like a particle. It's like the hole, right? I mean, it can move around. I showed you. I showed it moving. It can move around just like a particle. Okay. So this is remarkable. How could it be that we split an electron? You can't cut an electron in half, right? And that's not what we're doing. Electric charge is fundamentally quantized. Okay, you can't have half of an electron, but somehow we got away with this here. Okay, and I think this is truly amazing. Okay, this is one of the coolest things I ever learned, and actually I'm not the only one. So John Preskill is a very famous, distinguished theoretical physicist, someone I deeply admire. And but in addition to being a theoretical physicist, he moonlights as a poet. Okay, and so when he learns things that he's excited about, sometimes he gets inspired to write poems about it. And so he learned about something related to this when he listened to a talk by another distinguished theoretical physicist named Leon Valens, who's actually a good friend of mine. And so he got inspired to say it like this: you have to admit it's legit. Electrons can split. So something is truly amazing going on here. Okay, and so what is it? Okay, and so a clue to this, you can see that I started off with the electrons occupying the blue wells in the A phase, but in the middle they're occupying the red spaces, the B phase. Okay, and so this leads me to the essence of what topological states, electronic phases are. Okay, because what distinct topological phases allow is they allow the impossible to occur on their boundary. Okay, so on the boundary between the A phase of polyacetylene and the B phase, we have this impossible half of an electron. Okay, you can't have half of an electron by itself, but you can have exactly half of an electron on the boundary between these two topological phases. Okay, and so that is the essence of what topological insulators are about. They allow the impossible to happen on a boundary. Okay, and so the point I want to make is that this is just a simple example. There are many, many more examples of this kind of phenomenon. Okay, and I want to show you how interesting the impossible things that they allow are. Okay, and so I want to show you a bunch of these examples, and the first one I want to show you is really it's what started this whole thing, and it's motivated by a problem. Okay, and the problem is this: the flow of electrons in an electrical conductor is actually kind of disorganized. The electrons are constantly sort of bumping into each other. It's sort of like, a year and a half ago, I actually had the pleasure of traveling to India for the first time. I went to Mumbai, and it was an amazing experience. And one of the things that I got to experience when I went to Mumbai was the traffic situation there, which was an eye-opening experience for me. It's hard to get where you're going because you're constantly bumping into people, and it's hard to get around. Okay, so that's sort of the way electrons feel in an electrical conductor. Okay, and this problem gets even worse the smaller and smaller you try to make your electrical conductors. Okay, and so the question is there any way you can get around this problem? Okay, so one thing you might think is you might take a cue from how it is we try to organize traffic. Okay, and so one way that you can organize traffic is to make a divided highway. Okay, and on a divided highway, the flow of traffic is much more organized. Okay, you're not constantly running into the people coming towards you, and things can flow smoothly. Okay, and so the question I'd like to pose is whether it's possible to do this, something like this for the electrons. Okay, and I'd like to argue to you that with a topological phase of matter, this is indeed possible. Okay, and the topological phase of matter that allows this is, it's really the sort of mother of all topological phases. It's the state that we understood first, and it's the state that we understand the best. Okay, and it is called the quantum Hall state, okay, or the quantum Hall effect. And so what the quantum Hall state is it's what I'll call a two-dimensional topological insulator. Okay, and so two-dimensional, what I mean by that is it's sort of like, so the electrons are confined to a two-dimensional plane. Okay, sort of like a piece of paper is two-dimensional, right? And the electrons can only move around inside the piece of paper. Okay, and importantly, on the interior of this piece of paper, the electrons are sort of locked in place, like in an insulator. They're stuck. They can't do anything. Okay, but this two-dimensional insulator is characterized by a topological invariant, which is sort of like this genus that I introduced to you, which counts the number of holes in the donut. Okay, and what this integer topological invariant allows is that on the boundary of this insulator, if the integer is n, there will be n lanes of one-way electrical conductors, just like in a divided highway. Okay, and so these one-way electrical conductors live on the boundary of this topological phase. Okay, now these one-way electrical conductors are remarkable things. Okay, because if you're an electron, imagine you're an electron and you're in one of these states. Okay, then you have no choice but to go forward. That's the only thing you can do. Okay, so that means if you put in an electron on one side, you know with 100% certainty that it's going to get to the other side. Okay, so the transmission of electric charge in these edge states is perfect. Okay, now so let me tell you, if you could have one of these one-dimensional edge states, if you just had a one-dimensional wire that had just one of these one-way edge states, if you could have that, then think of what you could do. You could put the entrance inside your refrigerator, and the exit outside your refrigerator. Okay. And then you'd have a way of running your refrigerator without plugging it in, right? Because these edge states would carry heat from the inside of your refrigerator to the outside, and that's what a refrigerator has to do. It has to constantly pull heat out of the refrigerator. Okay, so if you could do that, you'd be rich. All right, you'd solve all the world's energy problems. You'd be rich and famous, but there's a problem. Okay, the problem is it's impossible. Okay, so having a single one of these, one-way edge states, in addition to violating, the no free lunch rule, it violates deep principles of physics. Okay, it's impossible. So these one-way edge states, they're impossible, but the topological phase, this topological insulator, quantum Hall state, allows this impossible thing to happen on its boundary. Now, in a sense, now, of course, you can't just have one boundary. You also have to have the other boundary. Okay, so this edge state can't exist without this one. So I can't just stick one of these into my refrigerator without also sticking this one in. Okay, and so that's how you get around this thing. Okay, and so in a sense, what this topological phase has done, it is taking a single one-dimensional conductor where the electrons can move both to the left and to the right, and it has split it in half, kind of in the same way I split the electron in half in polyacetylene. So it has split this indivisible one-dimensional conductor, and so now I have half of it, this impossible right mover and this impossible left mover on the boundaries. Okay, so that's what this has accomplished. Now, so this story that I've told you, it's actually a little bit backwards. Okay, so the quantum Hall effect was not discovered by people sitting by themselves, thinking about donuts and coffee cups and things like that. The quantum Hall effect was discovered in the lab. Okay, and this was one of the great discoveries of the late part of the 20th century, was the discovery of the quantum Hall effect, and it started with experiments by Klaus von Klitzing. And so at the time, this is in the 1980s, what von Klitzing was doing is he was doing fundamental electrical measurements on semiconductor materials. Okay, so he was studying the fundamental electronic properties of the semiconductor materials that now are components in your cell phone, electronic materials, electronic devices. Okay, so he was doing the fundamental characterization of those. And so one of the things that you do when you do that is you measure the electrical resistance as a function of the magnetic field, in a magnetic field. And so what von Klitzing observed was that as a function of the magnetic field, the electrical resistance had these steps, where on this step, the value of the electrical resistance turned out to be incredibly accurately quantized in units of these fundamental constants, this is Planck's constant and the charge of the electron. Okay, and so one way of saying this is that if you know this fundamental constant, which we know these constants pretty well, then you can measure the integer n to 1 part in a billion. So it's like 1.000, 9 zeros. Okay. Another way you can say it is that if you believe this has to be an integer, then that allows you a very precise way of measuring this combination of fundamental constants, measuring it to 1 part in a billion. So in fact, this is the most accurate way that one can measure this combination of fundamental constants. Okay, and a couple of years ago, the powers that be decided to change the way we define the fundamental units. Okay, in particular, the unit of mass, the kilogram. So, how do you define the kilogram? It used to be that there was some chunk of metal in France, locked in a vault somewhere. That was the kilogram. Okay, but a couple of years ago, it was changed to this experiment, which defines the kilogram. Okay, and so this is the origin of one of the standards of the units that we have, because it's so accurate. Okay, now, so at the time when this was discovered, it was a huge puzzle. How could it be that it was so accurate? Because, the thing is that this experiment was not a perfect experiment. So here's a picture. This isn't actually von Klitzing's sample, but it's sort of like it. Okay, and look at it. It's all dirty. There are all these like globs of solder, and it's all this dirt, and it's not a perfect sample. Okay, there's all kinds of dirt and mess. So how could it be that you have this crappy sample and you measure a virtually perfect conductance? Okay, how could that possibly be? Okay, and so that was a clue. And so that led geniuses in theoretical physics, okay, people like Bob Laughlin, David Thales, and also Duncan Haldane, who you heard from a couple of weeks ago. It led, geniuses in theoretical physics to think deeply about how this could be, okay? And out of this emerged the concept of topology, okay? And so David Thales recognized that, in fact, this integer that you measure by measuring the value of these steps is in fact this topological invariant that I told you about, that specifies how many edge states you have. Okay, and so this gives you some understanding of why it is that it could be so precise in such a crappy sample, because the integer, you can't mess it up by changing it a little bit. Okay. So maybe this sample is more like Dave the octopus than the sphere, but Dave the octopus still has a precisely quantized genus. Okay, and so that's how it is that this Hall resistance is so pristinely quantized. Okay, now you might think that this could be a pretty useful thing, having these one-way edge states to organize the flow of electrons. You might think that could be a useful thing for your electronic devices to, make the flow more organized. The only difficulty with this is that in order to get this to go, you need to put it in a big magnet. Okay, so if you look at the magnetic field here, it's, you need several Tesla of magnetic field, and a Tesla, in order to get a Tesla of magnetic field, you need a big, strong magnet. Okay, and, you don't want to have to carry that around in your pocket. Okay, so there's a question, might it be possible to get this to go, or get something like this without having such a strong magnetic field? And so this is a hard problem. Okay, this is something people are trying to do, but it's not so easy. So one possible direction to doing something like this is to use a different kind of material, which is called a topological insulator. Okay, and so now I want to introduce you to the topological insulator materials, which do something sort of like this. Okay, and the way I like to think of a topological insulator, so a topological insulator is a material, it's a three-dimensional piece of stuff, okay? It's an insulator on its interior, but it's a conductor on its surface. So the way I like to say it is a topological insulator is sort of like a chocolate treat that is wrapped in tinfoil. Okay, so I don't know if you have these in India. We have in America, we have these candies called Hershey Kisses, and then what they are is they're chocolate wrapped in a wrapper of tinfoil. Okay, and and so a topological insulator is it's an insulator on the inside. Okay, so the chocolate is like the insulator, and the wrapper is like the conductor on the surface. Okay, so it's an insulator on the inside, but the boundary is an electrical conductor. But there's something. This isn't quite. This isn't quite right, because actually, if you were to have this, then it would be a very frustrating chocolate treat, because if you tried to cut it open, it would still be wrapped. Okay, because this conducting surface has to be there. You can't get rid of it. If you cut it open, it would still, you'd have the surface, you'd have an inside surface, but the inside surface would still be wrapped. And the reason for that is that this conducting surface is impossible by itself. Just like the one-way edge state, I told you that was impossible by itself. Okay, the half an electron is impossible by itself. This conducting surface is also impossible by itself. It has a very specific special property, and I don't want to get into the technical details of this, but what we say is that it has this special property which is called a single Dirac cone on its surface electronic structure. So that's what this surface electrical conductor has, and this property is impossible in a purely two-dimensional system. Okay, and so that means that you can't peel it off. Right? If you could peel it off, if you could peel the conductor off, then you'd have it by itself. Okay, and but it's impossible. So this conductor has to be there. Okay, and this conductor has a very specific property. Okay, so now I told you that the quantum Hall effect was discovered in the laboratory, and then that led geniuses in theoretical physics to think about it, and then some understanding emerged from that. The story of topological insulators is actually a little bit different. Topological insulators were really sort of conceived and thought. Okay, and so the way this came about is it started off with thinking about what might be possible. Could it be, so we at the beginning we knew that the quantum Hall effect existed and that there could be two-dimensional topological insulators, and so then that posed a question: could there be a three-dimensional version of this? Okay, and so this led to some thought, and I played a small role in this, and so what it turned out is that we had this idea that yes, maybe it is possible. Okay, and in particular, we were able to predict specific materials which have specific electronic structures where this might happen. Okay. Now, so we did this. Now, if this is all that had happened, then it would have been kind of interesting, but it wouldn't have been that interesting. What made this really interesting was that these ideas were able to come to life in the real world. Okay, and so what that required people to actually make these materials. Okay, and so for example, it's possible to grow very high quality crystals of so bismuth selenide is one of the best topological insulator materials. And so one can grow crystals of bismuth selenide. And then once you have the crystals, you have to be able to demonstrate that they have this special property, this special impossible surface state. Okay, and so what people did is, what they basically did is they took a fancy picture of the surface of the topological insulator using a technique called angle resolved photoemission spectroscopy. And basically what that is it's taking a fancy picture of the surface that allows you to deduce what the electronic structure of the surface is. Okay, and so what this picture shows is it basically shows a textbook perfect Dirac cone on the surface of bismuth selenide. Okay, and so these experiments demonstrated that this real material, you can hold it in your hand, it's a real crystal, in fact has this impossible conductor on its surface. Okay, and so this discovery sort of opened the floodgates to nowadays there are many other kinds of materials that have these topological insulator properties, and there are many other versions of topological materials that we have as well. I'm not going to describe all of them to you, but this is an incredibly active subject these days. And the reason it's so active is a combination of the richness of the kinds of electronic structures that materials can have. There are many details, but there are many features that electronic materials can have. And it's possible to make lots of these things and study them in the laboratory and verify their properties and do things with them. Okay. Okay. So now, so before I finish, I want to introduce you to one more version of this idea of splitting the indivisible and coming up with an impossible thing on the boundary that hopefully we can do something with. Okay, and so the final example that I want to give you is motivated by another problem. Okay, and that problem is the problem of making a quantum computer. Okay, so let me first remind you what a regular computer does. So a regular computer does operations on numbers, okay? And numbers you can sort of represent as in terms of the binary digits, 0 and 1. So any number you can write as a bunch of zeros and ones. So for instance, 5 sort of looks like 101 in binary digits, okay? And so what a classical computer is, in simple terms, is it's some device where you input a bunch of classical bits, which are the zeros and ones, which maybe encode some binary number. And it does some operation on those bits and spits out some more bits, which encode the answer. Okay, so for instance, if this operation adds 2 to the number, then it spits out 7, which looks like 111. Okay, so that's sort of what a classical regular computer, like the computer that you have in your, that you're watching this on, does this kind of thing with classical information. Okay. Now, what quantum information is, so what quantum mechanics allows, okay, is that a bit, I can sort of think of a bit, it's like a switch. It's either on or it's off. It's something that can be in 2 different states, okay? And what quantum mechanics allows is that a quantum bit can be either 0 or 1, or it can be both of them at the same time, okay? And so this both of them is at the same time. This is called quantum superposition. And this is one of the mysterious features that quantum mechanics has, okay? And don't try too hard to understand what this quantum superposition means, okay? Because, frankly, I don't understand it. I don't think anybody really understands it. Now, that doesn't mean we don't understand quantum mechanics. I know the rules of quantum mechanics and how to use it, but those rules don't tell us what it means, okay? So that's a harder question. Okay, but it is a fact that quantum mechanics allows, bits to be 0 or 1 or both of them at the same time. Now, so think what you could do with this. Let's now suppose that you have a bunch of these quantum bits, which can then encode a binary number, a bunch of zeros and ones. So then if you can have them be both of them at the same time, then you can have a state of, say, several quantum bits, which is all of the numbers at the same time. Here I've written it down for 3 bits, which I have now a superposition of all of the 3-digit binary numbers going from 0 to 7. Okay. And so now, so you have a single state that has all the numbers in it. So now what a quantum computer would be, if you could make one, would be a device where you send in a qubit or some string of qubits, and you do some operation on them, and it spits out a string of qubits. Okay. So if you send in this state, which is a combination of all of the numbers, then what you get out is a combination of all of the answers. Okay. In one shot. So in order for a classical computer to do this, you'd have to do it for all the numbers. You'd have to do it 2 to the n times. Here you get it in one shot. So that's pretty good, right? So maybe this gives you an idea that a quantum computer could be more powerful than a classical computer. Now, if you think this is too good to be true, you're right. It is too good to be true. Okay. So there are subtleties that make it hard to extract all the information. Okay. So it's not as good as 2 to the n. Okay. But it is still good. Okay. It is a fact that there are classes of calculations that a quantum computer can do much faster than a classical computer. Okay. And so that is a great motivator for trying to make a quantum computer. Okay. Now, the problem is it's a very difficult problem. So this is one of the grand technological challenges of our time. Okay. And so it's a very hard problem. And the reason it is hard is because of a fundamental difficulty with quantum mechanics, which is that quantum superposition is extremely fragile. Okay. And so the problem is that if you have this state, which is a 0 and 1 at the same time, then if you look at it, if you measure it, you don't measure them both at the same time. What you measure is that it's one or the other. And it's sort of like flipping a coin, which one you get. Okay. And once you've measured it, it's not in the combination anymore. So this quantum superposition is destroyed by measuring it. Okay. So the problem is, in order to measure a qubit, you have to kill it. Okay. So this points to a practical difficulty with making a quantum computer, which is how do you keep the quantum computer from accidentally measuring itself? It doesn't have to be a person that measures it. Okay. So how do you keep a quantum computer from accidentally measuring itself and destroying all of the quantum information? So this is the big problem. So this is the decoherence problem. Okay, which is what makes processing quantum information so difficult. So one of the ways you can do this, in principle, is to have your qubits be just extremely isolated from everything else, so that there's no interaction between this degree of freedom which has your quantum information and any other degrees of freedom that you have them be extremely isolated. And this may be the best way to do it. Okay. There are lots of ideas that people have for how to do this. What I want to describe to you, though, is another idea for how to protect the quantum information, which takes advantage of a topological phase of matter. Okay. And the idea is to split the qubit. Okay. Just like I split the electron in two. Okay. It turns out that there exists a topological phase which is called a one-dimensional topological superconductor. Now, I don't have time to explain to you what a superconductor is, let alone what a topological superconductor is. But let me just say that the way we think about it is very similar to the way we think about topological insulators. It's very similar to this simple one-dimensional polyacetylene cartoon that I showed you. Okay, so those ideas really apply directly to this topological phase. And so what a topological superconductor allows you to do is it allows you to take a qubit. And remember, a qubit is like it's like an object that can be in two states. So it's like, so it exists in a particular place. So you can't have half of a qubit by itself. I mean, you can't split it in half. It's indivisible. But what the topological superconductor allows you to do is it allows you to split it and have half of a qubit sit at the ends of a one-dimensional superconductor. So it splits it in half in the same way that I split the electron in half. Okay? So the beauty of this is that if you can only do local measurements, if you can only look at one place at a time, these could be far apart. If you can only look at one place at a time, then it is impossible to measure the state that this qubit is in, whether it's 1 or 0. Okay? And that means that it's impossible for, your device to accidentally measure it. So the quantum information is topologically protected. Okay, so that's the big idea. Okay, so we call these states at the end, we call them Majorana end states, and they're sort of like half of a qubit. Okay, and so this proposal for using these topological superconductors to make what one might call a topological quantum computer. So this is another tremendous motivator for trying to make this come to life. Okay, and this is an extremely difficult problem. Okay, it turns out that you can't just go buy a topological superconductor. You have to figure out a way to convince nature to do this. Okay, but there has been tantalizing progress in this direction. Okay, and so for example, so one way people have thought to do this is to use a one-dimensional semiconductor material, indium antimonide, which one can sit on top of a regular superconductor, and to make a one-dimensional superconductor. And then they look at the end and they see something which has a little peak, and this little peak is exactly what you'd want to see if you have this half of a qubit sitting at the end. Now, the difficulty with this is that you have to rule out all the possible less interesting explanations for what this peak might be. Okay, and so this is still, I think this is not completely a done deal yet. There's still active debate going on about whether in these experiments or others that are like it, there are many other systems that exhibit similar types of phenomenon, whether we've really isolated the Majorana end state. Okay, and then even on top of that, there's the challenge of actually, once we know we have them, how do we harness them and actually demonstrate that they can store quantum information and then possibly manipulate the quantum information for a quantum computer. Okay, so there's a long road there, but this is a very exciting road to go down. Okay, so I think I'm probably running out of time. So let me just leave you with a thought, which is, we know pretty well what the building blocks of matter are. Okay. Of course, one could always dig deeper into what the fundamental building blocks are, but as a practical matter, we know quite a bit about what the building blocks of matter are. But that's only part of the story. You see, there's also a very interesting part of the story, which is what you can do with the matter, what the matter, that obeys those fundamental rules, what that matter can do. Okay. And in order to understand what matter can do, you really need sort of organizing principles. And so let me give you an analogy, which is, Newton discovered his laws of classical mechanics, in the 17th century. And, Newton's three laws basically had it all. Okay. All of classical mechanics is sort of in those laws. Okay. But it was only, almost 200 years later that the concept of energy emerged as an organizing principle for understanding how matter that obeys Newton's laws can behave. Okay. And, of course, in the modern day, energy is an organizing principle for not just physics, but all kinds of branches of science and humanity, right? And so the point I want to make is that quantum mechanics is sort of in a similar situation. The laws of quantum mechanics were set out in the early part of the 20th century, and they're still right in the same way that Newton is right. Okay. But organizing principles for how quantum matter, obeys, how quantum matter behaves, are still being uncovered. These concepts like topology. Okay, and that makes it a very exciting time to be a physicist, because new things are happening, new ideas are emerging, new kinds of materials are being discovered, and there's a lot of interesting, amazing things to uncover. And so I'd like to just leave you with the with the idea that matter can arrange itself in the most ingenious ways. So thank you very much.
Thank you so much, Professor Kane. That was an incredible talk. So I think let's have a round of applause for Professor Kane's incredible lecture. Professor Kane, will it be okay if we take a few questions which have been typed by people on the chat?
Certainly. Now, should I stop my screen share now, or?
Yeah, I guess so. I mean,
okay.
Yeah.
Good.
Okay. So let's see. Okay, here we go. So, okay, so there is a question which says, this is a question by Rapsan, and the question is, how does the whole move from one atom to another atom?
Well, that's a great question. So the way it moves is by, actually, let me share my screen again, because I can show you this. So it moves by having an electron take its place. Oops. Okay, so here's the hole. And so this hole can move by having an electron move. It's as simple as that. So does that answer the question?
Okay. Yeah. Thanks. Okay, great. So so there is another question by Arnab Chauhan, and the question is, how do we define topologically inequivalent insulators on an electronic scale? Is it like the energy gap would change?
Yeah, well, no, it's so so as you deform, as you change an insulator, the energy gap can change. Okay, but it has to remain finite. It can't go to zero. So what happens if you, let's imagine, let's imagine you do some process which turns a trivial insulator into a topological insulator. So it changes the topological invariance. So then the statement is that you have to go through a point where the energy gap goes to zero. And that point where the energy gap goes to zero, that's a critical point. So that defines a quantum phase transition, okay, where the energy gap goes to zero. So for example, in this polyacetylene example that I gave you, in order to go from this to this, if you go through the point where all the bonds are the same, then this energy gap goes to zero. And basically what that means is that the electrons can sort of, they can sort of slide, it doesn't matter. They don't care whether they're in the red or the blue spaces, so they can sort of slosh around. Okay. But in terms of the energy gap, the quantum phase transition occurs when the energy gap goes to zero, and something special happens there. And so insulators are topologically the same if you can deform them into one another, keeping it an insulator the whole time.
Excuse me, sir. Sorry for interruption.
Yes.
Yeah, I was disconnected, and my question was, why all the electrons have the same mass and same charge? Are they like kind of entangled in themselves?
Well, yeah, that's a very deep question. Okay, why do they all have the same charge? And frankly, that's a question for that's the kind of question where if I gave you an answer, then you could say, well, why is that?
Yeah, okay.
And you could keep going. You could keep going. No matter what I said, you could say, why is that? And so look, that doesn't mean it's not interesting to go levels deeper. Okay. And so one can, so one thing one can imagine is that could it be that the charge of the electron is a kind of topological property that the electron has? That's like that this quantization of the charge is quantized for the same reason that topological invariants are quantized. Okay. Yeah. And so Dirac, famous theoretical physicist, is famous for having ideas like that. Okay. So it is interesting to go to dig deeper into the reason why these facts are the case. But I've been sort of going in the opposite direction. I've been saying, let's suppose we start with these building blocks and we start with the rules that the building blocks obey. And then what happens when you go up and make things out of those building blocks? Okay. And so that's a different, so those are going in different directions. Okay. And one point that I want to make is that you could dig down in more fundamental, but it's kind of hard to imagine ever getting to the bottom.
All right, great. So I would request all of us to keep the questions in the chat because we do have a time constraint. And okay, so there is a question which says, can't we say that the single electron is delocalized throughout the chain rather than saying it is split into fractional charges at the boundary? This is a question by Nawaf.
Well, okay, when you say the single electron, I mean, so certainly you can describe, if we're describing this, this thing here, you can describe it in terms of electronic states that are delocalized across the entire chain. In fact, you can describe an insulator where all the electrons are locked on their atom. You can describe that in terms of electrons that are plane waves, electrons that are extended, but it remains the fact that there's an energy gap that locks them. That there is an energy gap which makes it so that the insulating state is electrically inert. Okay, and so this half of an electron, it's really made out of all of the electrons. Okay, so it's a collective property of the ground state of all of the electrons. Okay, and so you can't really think about this thing as a property of a single electron. It's really property of all of the electrons. Now, of course, the whole system is made out of a whole bunch of single electrons. Okay, and so there is a description of this that one can make, in terms of single electron states. Okay, but I don't think those two pictures are incompatible with each other.
Okay, so there's a question by Shubham Rastogi. The question is, what is in the boundary of the topological phase that electrons can move in a lane? That's, I think, referring to a slide there.
Yeah, well, so what's in the boundary? So what is happening at the boundary? So if you think, so I told you that the only way you can go from a topological insulator to a trivial insulator is if the energy gap goes to zero. So now what you can imagine is, this quantum Hall state, the thing that has the non-trivial topological invariant, that's a topological insulator. The vacuum is like a trivial insulator. So the vacuum is an insulator too, okay? And so now you can imagine what would happen if, as a function of position, I try to slowly interpolate between the topological insulator and the trivial insulator. So then somewhere along the way, the energy gap has to go to zero and there has to be a conducting state. So that's what's happening at this edge conductor. Okay. Now, one has to go into a little bit more detail to understand why that edge conductor is a one-way edge conductor. And I can't give you a simple way of saying that. I mean, without going to a little bit more technicalities. But but it's not difficult to understand why there has to be a conducting boundary. Okay, because in order to interpolate between the topological insulator and the vacuum on the outside, you have to go through a conductor. Okay, so I think that's probably the simplest thing that I can say.
Great. And now there are two queries on the portion on qubits and split qubits. So first, by Gaurav Datta asks, what is the value of half a qubit? Is it 0 or 1, or is it again a superposition of 0 and 1?
Well, that's not even a question that I can ask. I mean, half a qubit doesn't have well, let me say, it's impossible to have an odd number of half qubits. Okay, so just like in the polyacetylene, it's impossible to have an odd number of these. Okay, they have to come in pairs. Okay, and so it doesn't make sense to talk about the state of a single half qubit. And and I guess what I would say is that the reason that so how could it be that this qubit is somehow delocalized and lives in two different places? So this is coming about because of the highly non-trivial quantum entanglement that arises in the superconducting ground state. Okay, and so that allows somehow this this single state to be sort of shared by two places. Yeah. So, but the state of a single Majorana, that isn't a well-posed question.
Okay, and there's I guess there's another question sort of related, which says, how could we it asks, says by Shivani Yadav, and the question is, how could we combine the split qubits again to do the final measurement?
Right. Okay, that's a very good question. So, so in order, so if we keep these Majorana end states apart, then it's impossible for the computer to accidentally measure itself. It's also impossible for you to measure it. And so in order to do the measurement, you have to be able to move them into proximity with each other or somehow couple them together. Okay, so maybe that means you want to physically move them, or maybe it means you want to somehow arrange it so that you can increase the coupling between them. So what happens when you bring the two together is that they're basically the two states can get split. Okay, and then you can measure which one it's in. Okay, whereas when they're far apart, then you can't tell which one it's in. So what's necessary in order to have a readout of the quantum information is that you have to have a way of bringing them together. And you also, you also have to have them be together in order to initialize the state. Okay, and so what you can do is you can have them start off together. And then they're in a known state, the qubit is in a known state, then you separate them, okay? And then it stays in that state, but now that information is protected. And there are ideas about how one, even when the qubits are separated from each other, you can do operations on them by sort of moving them around each other, okay? And by moving them around each other, you can do some operations on these qubits, which are what a computer is supposed to do. Okay, and that's part of it. It turns out that in this topological superconductor setup, you can't do all of the operations that you'd want to do for a universal quantum computer. You can't do them all by doing this braiding of the Majorana particles, but you can do some of them. And there are ideas for more exotic types of topological qubits where you could do all of them, or maybe there are ideas for other protocols that you could do to do the missing operations.
Okay, I skipped this question. There was a question by Shivam Miglani, and the question is on how is the Dirac cone and 3D topological insulators formed?
Well, it's the same sort of thing where if you, so what I can say is that the topology, if I try to interpolate between the topological insulator and the vacuum on the outside, then the energy gap has to go to zero. And this three-dimensional Dirac cone is the energy gap going to zero. Okay, that's what, so a cone has a point. Okay, and the point of the cone, and what I mean by a cone, it's a cone with both a cone on the top and a cone on the bottom, sort of like an hourglass, right? And that point where the two ice cream cones touch each other, that is the vanishing energy gap. Okay, and so what happens as you go into the topological insulator is that energy gap becomes finite. Okay, so that Dirac cone has to be present on the boundary, and it really is the same. The same sort of thing happens with the one-way edge states as well. It's the same sort of phenomenon.
Great. I guess I would take the liberty of squeezing in one query of mine,
Okay.
which is more math oriented, because I'm very intrigued by the existence of these topological invariants, which you talked about. So my simple query is this: that, for example, the examples that you talked about, this 2D quantum Hall effect, I'm going to be displaying my ignorance of the relevant kinematic physics, but that's how it is. So I mean, I'm assuming that these topological invariants are actually related to some characteristic classes in math. So is it like there is some kind of a curvature form which is
Yes, absolutely. Yeah.
integrated
So,
over some cycles to give
absolutely.
you
So the integer quantum Hall effect is described by the first Chern class.
the okay.
Okay.
And what is the
what it
curvature
is,
form? How do you define the curvature form to get you that?
so what you have is you have a so what a band structure is it's a quantum state which is defined as a function of momentum, as a function of a two-dimensional momentum. So the momentum is defined on a torus, okay? So it's a two torus. So I have a quantum state which is a function of which is defined on a two torus. So it's a function of position on the two torus. Okay, and so that defines a vector bundle on this two torus. So it's a quantum phase. So it's a complex vector bundle on the two torus, and a complex vector bundle on a two torus is characterized by the first Chern class.
Okay. So, I mean, does it depend on what is the ambient dimensionality, or is it always?
Yeah, it does. Yeah. So in two dimensions, there's the first Chern class. In three dimensions, there's no Chern class.
Yeah, exactly. That was
in four dimensions. There is a Chern class. So you could have a four-dimensional quantum Hall state.
Okay.
And so this is the reason why people didn't think there was anything, that people thought that, well, the quantum Hall effect is all there is. Okay, because there's no Chern class in three dimensions. Okay, so that says there shouldn't be any three-dimensional topological installation. So the new thing is that symmetry, in particular time reversal symmetry, refines the topological classes. And so it turns out that with time reversal symmetry, there's a different topological invariant, which turns out it's only a Z2 topological, and it only has two values, which distinguishes the three-dimensional topological insulator from a trivial insulator. So it's a different kind of topological insulator. The mathematics that one uses to do that, I think, goes under the heading of K theory.
Okay. All right. Thanks. Thank you so much. So I think with that, we come to the end of this incredible lecture of Professor Kane, and with his equally incredible patience with all the queries. We really appreciate it. Thank you so much once again. And thanks everybody for joining in. And thank you. So thank you so much.
Okay, it was my pleasure. Okay.
All right. Bye-bye. Stay safe.